Okay, so today I want to talk about a class of objects that are, in some sense, very familiar, and in other ways not. So the sense in which they're familiar is because they're quite intimately related to what you would normally think of as Green's functions. However, they're rather different from Green's functions because they really have to do with operators and their properties. And this is the idea of the resolvent operators. So our learning goals for today is to define what I mean by the resolvent and explore some of their properties. And I'm going to focus on the properties that will allow us to generalize the Kashi formula. So the Kashi integral formula, relates the integral of some function divided by a polynomial to its residue at the poles of the integrand. And we want to generalize this to matrix valued functions and operator valued functions. And this will lead us to the definition of a set of projectors. And whenever we have projectors and we have a complete set of projectors, then we know we have what's called a resolution of the identity. In other words, we can take the identity operator and expand it in some way in terms of these operators, projectors. So that's where we're going today. And let's get started then. So our story starts with the idea of the resolvent. So we'll start then with some operator, which I'm going to call T. So let T be some operator with some spectrum sigma of T. Let T be an operator with spectrum sigma of T. Now, you'll recall from our previous discussions that what we mean here is I give you some operator. I solve the eigenvalue problem for this operator, and I find all its eigenvalues. Once I have all the eigenvalues, I form a set of these eigenvalues, and that set of the eigenvalues is what we will call the spectrum of T. So suppose I have some operator T, and I have a spectrum for that operator T. For that operator, which I'll call sigma of T. The operator, the associated operator, which I'm going to call R subscript lambda of T, and which I'm going to define as T minus lambda inverse is the operator that we're going to call the resolvent of T. Okay, so it's essentially 1 over T minus lambda. Okay, but because we're dealing with matrices and operators, we don't talk about 1 over, we talk about the inverse. So T minus lambda inverse. Okay, so this is the resolvent of resolvent of T at lambda. And key in this definition is that lambda cannot be in the spectrum of T. Okay, so note here that this lambda is not in the spectrum of T, because otherwise we'd be dividing by 0 in some sense. Is everybody with me as to what the definition of the resolvent is? Okay.
Yes.
So now you see, if you recall the way we defined operationally anyway, the way we defined the Green's function associated to a particular differential equation, right? The Green's function was defined as the operator inverse of the differential operator. So then it makes sense to think that perhaps this guy here, the resolvant operator, might be related in some way to the Green's function associated to the differential equation T psi equal to lambda psi or whatever. Well, not lambda, but another Greek letter, psi. Right. So we're going to explore this in some more detail in what follows, and I'll show you exactly how it's related to the Green's function. But first, let's unpack this definition a little bit and see if we can use it to deduce some properties of the resolvant operator. Okay, it's a very important operator for analyzing the spectrum of operators, of differential operators, for example, like T. So it's worth spending a little bit of time and unpacking this. So suppose I have an operator like T, and I have some numbers, possibly complex numbers, lambda and mu, that are specifically not in the spectrum of T. So suppose that lambda and mu are, neither of them are in the spectrum of T. And in particular, I would like lambda and mu to be different from each other. Okay, so we're going to use the definition then of the resolvant to deduce some properties that are going to be useful in what's going to come. So the first property we're going to explore follows from the following fact. So we'll start off by making a note, and then we'll see immediately how from this note so note the following. Note that if I take R lambda of T, which remember is T minus lambda inverse, then I can write this thing as R lambda of T, R mu of T, provided I act from the right with T minus mu. By the way, when I write down something like T minus lambda or T minus mu, I really mean T minus mu times the identity, or T minus lambda times the identity. Okay, so mu and lambda are numbers, but because T is an operator and I have to compare like with like, I have to multiply this by the associated identity matrix or identity operator. So that's the first point. Is this point clear to everybody? R mu of T times T minus mu is just the identity. Are we good?
Yes.
Would anybody like me to explain this? It should be fairly obvious. Okay, similarly, I can write R mu of T as R mu of T times R lambda of T times T minus lambda. Again, the reason I can do this is because these guys here are just the identity operator. Okay. Okay, so now it should be fairly clear that if I take the difference between R lambda of T and R mu of T, then I can write this as a product of R lambda and R mu by using the two identities that I just wrote down. In other words, property number one is that R lambda of t minus R mu of t is just lambda minus mu R lambda of t times R mu of t. So this ability to write the sum, with the minus sign, of two resolvent operators as the product of those two resolvent operators is going to be very important when we have large sums of resolvent operators, for example, in Taylor series expansions, right? Can everybody see that this is kind of obviously true? Good. Okay, so that's the first property that we're going to need. The second property follows from the fact that if we differentiate a resolvent operator, we can relate it to a product of resolvent operators as well. So the second operator follows from the following note, following observation. So note the following. So if we differentiate then with respect to lambda, the parameter in the resolvent operator, so I'm differentiating R lambda of t with respect to lambda, then this is just d by d lambda of t minus lambda inverse, which is t minus lambda to the minus 2 actions of the inverse. And the minus sign is accounted for by the minus sign in front of the lambda, which is just 2 actions of the resolvent. Okay, and you can show that similarly, n derivatives of the resolvent operator is just n factorial times R lambda to the n plus 1 of t.
Sorry, Jeff.
Mm-hmm.
I didn't quite get the last line from the last page.
Which part? Here to here.
Yes, I want to quickly copy that.
Oh, you didn't write it down. Oh, sorry. You done?
Yes, I'm done. Thanks.
All right. So similarly, we can show that n derivatives of R lambda of t is just n factorial times R lambda to the n plus 1 of t. Okay, so this is an important relation. And again, it's going to be important in formulae in which, sorry, let's try that again. It's going to be important in formulae in which we are going to need to take multiple derivatives of a resolvent operator. For example, the Taylor series expansion. Okay, very good. So let's do that then. So then, supposing our Taylor series expansion exists and that it converges, we can expand a particular resolvent operator in lambda about another number, let's say mu, as follows. So the Taylor series expansion about mu of the resolvent R lambda of T is the following. R lambda of T is just plugging into our definition of what the Taylor series expansion is, forgetting about the fact that we're dealing with operators, etc. So this is the sum from n equals 0 to infinity, lambda minus mu to the n over n factorial times the nth derivative of R lambda of T with respect to lambda and evaluated at lambda equals mu. But as we've seen just now, we can write the nth derivative of the resolvent in terms of powers of the resolvent. And so it should be clear then that this is nothing but the sum n equals 0 to infinity of lambda minus mu to the n R mu to the n plus 1 of T. In other words, the Taylor series expansion for a resolvent operator is particularly nice because it just is a power series in the resolvent operator, as opposed to having to differentiate the resolvent operator at each term. So that's neat. Yeah.
Is it the last sum? Is it R mu or R lambda?
R mu, because I'm evaluating. I have to do the evaluation at lambda equals mu.
Oh, wait, lambda is okay. Thanks.
Okay.
Can I ask a question, please?
Certainly.
When you in the first sum, is the derivative for by the d there just two lines? Is that an n or an n? I mean, is that an n or like two lines?
This.
Yeah.
It's an n.
Oh, sorry. I just saw two lines. I thought something weird was going on.
Nope. Any other questions? None? Okay. All right, so let's use these properties now to explore a very important theorem in operator theory called the spectral decomposition theorem. Okay, so to that end, so I want to see how these things can be used. To explore the so-called spectral decomposition theorem. Okay, so to that end, let's suppose we start with some. Let's work in a finite dimensional setting. So instead of thinking about this thing as a differential operator, let's just think in terms of matrices. So suppose I have some n by n matrix A with some complex number lambda, and I'm going to choose the complex number lambda in a very particular way. I'm going to first solve the eigenvalue problem for A, right? And I'm going to list all the eigenvalues for A, and then I'm going to pick some lambda such that it is bigger than any of the eigenvalues of A, right? There's a theorem in operator theory that guarantees us that we can do this, that we can always pick a lambda such that mod lambda, because it's possibly a complex number, is bigger than the biggest eigenvalue of A, or in particular the norm of A, right? The matrix norm of A. And then we can use this to make an expansion of the irresolvant operator. So let's write all of that down. So suppose that A is an n by n matrix, and lambda, possibly complex, is bigger than any of the eigenvalues of A. Then mod lambda is bigger than the norm of A, and we can make an expansion of R lambda of T as follows. So this is, R lambda of A. So by definition, this is A minus lambda inverse, which I can write as minus 1 over lambda times the sum over n equals 0 through to infinity of A divided by lambda to the n. Okay, so notice the fact that because this is a power series in 1 over lambda, this is actually the Laurent expansion for the resolvent. Okay, so not the Taylor expansion, which would be in positive powers of lambda, because this is an expansion in negative powers. This is nothing but the Laurent expansion of the resolvent. Well, if I have the Laurent expansion of some function, then I can immediately read off what the coefficient of 1 over lambda is as the residue of that function. So this is great because I'm being able to bring in complex analysis into this. Okay, so this means that the coefficient of 1 over lambda is just the resolvent, is just the residue of the resolvent. In other words, the residue of the resolvent which, pretending that we're dealing with ordinary functions, is just 1 over 2 pi I times the integral over some curve that's centered on the origin and large enough to enclose all of the eigenvalues of A, of R lambda of A d lambda. And this is, reading off what the coefficient is, just 1, because the coefficient of 1 over lambda takes place at, sorry, it's minus 1. The coefficient of 1 over lambda takes place when n equals 0 in the above series, which allows me to read off that coefficient as minus 1. So just one point to note here is that this circle, or this curve gamma, this closed contour, I will pick as a circle centered on the origin and enclosing all of the eigenvalues. Of the n by n matrix A. Okay. Now, this is nice, but it turns out that you can actually do more. And by you, I really mean you. So let me leave you with an exercise. Where I would like you to use a similar argument and show that this formula that we've just written down here is actually a special case of a more general formula. And the more general formula is the following. The more general formula says that if I take the closed contour integral over the contour enclosing all of the eigenvalues of the matrix A of lambda to the n of R lambda of A, and I integrate with respect to lambda, and then I divide by minus 2 pi I will simply get the nth power of the matrix A, where here n equals 0 is the case we studied just now, but n can also equal to 1, 2, 3, etc. Okay, so this is pretty neat actually, right? It says that I have an integral representation of the nth power of a matrix. Or equivalently, if I integrate the resolvent of a particular matrix with respect to the parameter lambda, multiplying lambda to the n, then I can express this integral as a power, quite simply, of the matrix itself. So let's see why this would be useful to know, other than the fact that it's just a really cool integral. Well, if I have the nth power of lambda, it should be fairly clear that if I have some function that has a convergent power series expansion, let's call this f of lambda, then this expression means that if f of lambda has a convergent power series, lambda here, remember, is just some number. Then what I have is that minus 1 over 2 pi I times the integral over gamma of f of lambda times r lambda of A integrated with a spectral lambda must converge to f of A. Let me write this in a more enlightening form. Simply put, 1 over 2 pi I times the integral over the contour gamma of f of lambda over lambda minus A d lambda is f of A. Now, if you go back to your complex variable theory notes, you should recognize that this is nothing but a generalization of the Kashi integral formula, only now this is an operator. So we have managed then, using the idea of the resolvent, to generalize the Kashi integral formula for operator valued functions. Kashi integral formula. Isn't that cool? Okay. Any questions?
Yes, I have a question.
Go for it.
On the previous slide, at the top, you make the statement that lambda element of complex numbers needs to be bigger than any of its eigenvalues, and then you say that the mod of lambda must be greater than the norm of A. Is that just a necessary condition that we need to have in order to write the Laurent expansion?
Yeah, I need the Laurent expansion to converge to the resolvent. So if I have an n by n matrix and lambda is selected to be bigger than any of its eigenvalues, then there's a theorem in operator value theory, operator theory that tells me that mod lambda is greater than the norm of A.
Okay.
Okay. I'm not proving that theorem, but I'm just stating it, and I need that in order to guarantee that my power series in 1 over lambda will converge.
Right.
Okay. Okay, so we managed to generalize the Kashi integral formula. So how do we use this formula? Well, why is it a useful thing to know? Okay. So to use the formula, I need to know some of the analyticity properties of the resolvent operator. So let's see if we can use what we know about the inverse of a matrix to say something about this. Okay, so let's think about this. A is some matrix. A minus lambda is also a matrix. It's a matrix in which I've taken off a lambda from each of the elements on the diagonal of A. And then I find the inverse of this thing, which is also going to be a matrix. So let's look at the matrix components of the inverse of A minus lambda. So note the following. R lambda of A has components, and the ijth component of this guy, by definition, is the ijth component of A minus lambda. And now let me make things explicit here, times the identity, and take the inverse of that. So this is the ijth component. So given a particular matrix, we know from first year already that if I want to calculate the inverse of that matrix, what I need to do is take the cofactor matrix and divide it by the determinant. In other words, this guy is just Cij divided by the determinant of A minus lambda times the identity. Okay. So note the following. The cofactor is just a function of lambda. In fact, it's a polynomial in lambda. I'll write that as Cij of lambda. So just make a note here. This is the cofactor of the ijth element of A minus lambda I. And this is divided by some quantity, which I'm going to call P of lambda. P of lambda is the determinant of A minus lambda I. But of course, that must also be some, and in fact, that must also be a polynomial in lambda. So both Cij and P are polynomial in lambda, which means that their ratio, the resolvent, can only be a rational function of lambda. In other words, the only singularities that the resolvent is going to have are poles. Is the argument clear? So because these two guys are polynomials in lambda, the ratio of those two polynomials must be a rational function of lambda implies only poles as singularities. And poles are given by the zeros of the denominator. In other words, the zeros of the determinant of A minus lambda. But those values of lambda for which the determinant of A minus lambda are equal to 0 are nothing but the eigenvalues of A. So the poles, the singularities, of R lambda of A occur precisely at the eigenvalues of A. So let's take the complex lambda plane. Any questions about this, by the way? So let's take the complex lambda plane. And I want to consider all of these poles, and in particular, remember we chose the contour gamma such that it encloses all of these poles. So if I have poles at various locations on the complex lambda plane, then the curve gamma is selected to be the one that encloses all of these poles. So this would be gamma. Okay, and these are the singularities.
Isn't gamma
Yeah.
centered at the origin?
Gamma is centered at the origin, but I'm just drawing a picture here. And I don't
Okay.
really care about, I can move I can translate all of these poles so that gamma is centered on the origin. That's fine. Okay.
Okay, thanks.
The key point here is what I want to do next, which is I want to deform gamma to the following. I want to deform gamma such that I enclose each of these poles with its own little gamma circle centered on that pole. I'll call each of these guys little gamma 1, little gamma 2, etc. Okay, so here what I've done is I've deformed contour of integration. Okay, and I deform it in such a way that I maintain the orientation. Okay. So what this means is that when I do that, remember, I found that since the residue was 1, this is just the sum over, let's say, k equals 1 to n for n poles of the closed contour integral over each of the gamma k's or lambda of a d lambda, which I'm going to choose to write as the sum over k equals 1 to n of pk. And my claim is that, in other words, take a step back. We're writing 1 as the sum from k equals 1 to n of some operators pk. So p1 plus p2 plus p3 plus p4, etc. If I can show that the set of pk's form a set of orthogonal projectors, then this gives me a resolution of the identity. In other words, the ability to expand the identity into the sum of these projections, these projectors. And so anywhere I can stick an identity, I can expand it as a sum of these projectors. Okay? So the question then comes down to, is this a projector? Or projection operator? Okay. If it is, then what we have on our hands is a resolution of the identity. So now let's do an example. And it's going to be a very useful example because it's going to demonstrate for us that indeed these things are, in fact, projection operators. I need the space, so let me write it here somewhere. So the question is, yeah.
I just wanted to ask, when we deform gamma into the little gammas, do we still essentially have those little bridges that cancel each other out?
Correct.
Okay, so you just haven't chosen to put them.
Yeah, I can basically, I have to connect each of these things by some info. Okay, so the point is I deform, right? So I'm not allowed to cut the curve. So what I've done here when I've written this down is, in principle, there's parallel lines, right, that go like that and like that. And they give you equal and opposite contributions to the integral. So they cancel out.
Right.
Okay, that's what you mean, right?
Yeah.
Yeah. Any other questions? Okay. So let me do an example to show you how this would work. So in my example, I want to check if these PIs are, or PKs are indeed projectors. So the problem is that this is a little bit tricky, right? Because these are essentially complex integral operators. They're integral operators, the PKs, right? But they're also complex. And we haven't really encountered two-dimensional complex integrals before. We've encountered two-dimensional real integrals, okay? But not so much two-dimensional complex integrals. Typically, we think of the complex plane as a, it's got one complex dimension. So it's thought of really as a line. And so that's why you do contour integrals, which are generalized line integrals. So they're all one-dimensional, one complex dimension. This is going to involve two-dimensional complex integrals, right? But while we haven't really encountered objects like this before, we have some intuition with what should happen with two-dimensional real integrals. And this intuition will come into play just now. So I want to start by recalling what the defining property of a projection operator is. Can anybody tell me, when do I know if I have a projector? Let's pick on somebody. Sebastian.
To be honest, I'm not 100% sure, but
so think about your experience with projection matrices. Yeah, 2x2 matrices that project, for example, a point onto a line or something like that. You have some intuition for this? Let's pick on somebody else. Justin.
I want to say it's something to do with the dot product, but I'm not sure.
It kind of is, but the dot product is usually taken with vectors. I'm talking about matrices, but
like element-wise product, I don't know.
Anyone else? William?
Yeah, I'm also thinking about the dot product in the sense that if you have a vector, you can project it, or you can write the projection of it using you can write the projection of it onto another vector using the dot product, but that's the only context in which I've really used the term projections.
Okay, let's try one more. Cabello.
I'm trying to quickly Google it, hoping that you don't ask. But I really can't think of anything.
You should just Google it first and then just tell me, like, with confidence.
Okay. No luck here. No luck here. Projection matrices, the ones I'm finding are like the standard like transformation matrices.
Okay, so here's the deal. If I take a point and I project it down onto the x-axis, say, so I take some point and project it down onto the x-axis. Okay, this is the kind of projection that you would have seen before, right? The key point is, if I apply that projection matrix twice, it doesn't do anything more. I can only project down a point onto the x-axis one time. That means that projections like that projector onto the x-axis satisfy that p squared equals p. So if I give you a matrix, any matrix, right, and it satisfies the property that p squared equals p, then you know that matrix is a projection operator. Okay? More generally, if I have a set of these guys, if I take any one of them, pi, and I multiply them by some other one, pj, then this must be delta ij, pj, with no sum implied on the indices. Now I want you to think a little bit and tell me if this makes sense with regards to what you've thought about before. Okay, very good. So what I have to show here is that for the operator that we have, for this integral operator that we have, pi, pj is delta ij, pj. So I'm going to show the case I equals j, and then I'm going to leave for you the case I not equal to j. So let's show let's take I equal to j. Okay, in this case, pi pj is just pi squared, which is 1 over 2 pi I, it's actually minus that, squared, times the integral over some curve gamma, I'm going to call it gamma lambda, which is associated to the operator r lambda of a, integrated with respect to lambda, multiplying another integral over the curve gamma mu r mu of a times, integrated with respect to mu. So that's what I mean by p squared. Okay, I've just taken two of these guys. So without any loss of generality, I'm going to choose lambda not the same as mu, and I'm going to arrange for the curve gamma, the curve gamma of lambda, is gamma lambda, to be outside the curve gamma mu. So we're going to choose lambda and mu to be different, and gamma lambda outside gamma mu. It could be enclosing gamma mu in its entirety, etc. But the point is that it's outside. So then we have the following. P squared is equal to minus 1 over 2 pi I squared integral over gamma lambda integral over gamma mu r lambda of A r mu of A d lambda d mu. Now I have something that I can use the properties that we explored right at the beginning of this lecture, because I have the product of two of these guys. So I'm going to take this product and I'm going to write it out as the sum or the difference, as the case may be. So this is equal to minus 1 over 2 pi I squared times the integral over gamma lambda times the integral over gamma mu of r lambda of A over lambda minus mu minus r mu of A over lambda minus mu. So this I get from property 1. D lambda d mu. Okay. So let's take this double integral and split it up into the iterated product of integrals. So this is equal to minus 1 over 2 pi I squared times first integral over gamma lambda r lambda of A d lambda integral over gamma mu d mu over lambda minus mu. That's the first one. Minus integral over gamma mu of r mu of A d mu integral over gamma lambda d lambda over lambda minus mu. Okay, so what can we say about these things? Well, the first thing we note is that in this integral, lambda lies outside of gamma mu. Remember, we chose the contour gamma lambda to be outside of gamma mu. So lambda is outside of gamma mu. On the other hand, in this integral, mu is inside gamma lambda. Okay, so what does that mean? It means that if I use the Kashi formula, this first term is going to give me 0 because I have the integral of an analytic function over a region that doesn't include a pole. Gamma lies outside of gamma mu. Lambda lies outside of gamma mu. On the other hand, because mu lies inside the integration curve, the integration contour, the lambda integration contour, this is going to give me a residue of just, 2 pi I times the residue. So this is just going to give me a factor of 2 pi I. So if I put these two things together, this tells me that this is nothing but -1 over 2 pi I squared times 0 from the first integral minus 2 pi I times the integral over gamma mu r mu of A d mu, which is simply pi itself. And so to go back, we started off with pi squared. We evaluated the integrals, and we found that this comes back to pi. As an exercise, I would like you to show the remaining case. Pi pj is equal to 0 for I different from j. Okay, so that's all I had to say today. Next time, I'll show you the actual spectral decomposition of A in terms of these projections, and we'll work out some examples.
Can we please go back a slide?
Certainly.
Thanks.
Any questions?